Alright, good morning calc friends, or maybe good afternoon if you're seeing this after noon. Our mission today is to solve exponential equation application problems. And the way I've structured the lesson is to do sample problems or example problems just like the ones you're going to have to do for homework. So for example, this first problem is similar to the ones that you see in 7 through 14 on your assignment that I'm going to give you today. And so we have A is going to be like that one, B, and I think there's a C on the next page. So I'm going to number the types of problems that are, or number the problems that are on your homework right here, and the problem that I have here for you in the notes is just like the problems that are here from your assignment. So without further ado, let's get started. So we're going to use the continuous interest formula to find missing quantities. So in your homework assignment, you're going to have a table, and you're going to have to fill in various parts of the table. So I've taken one line of the table and put the information here, and down here I've done a different line of the table and put some information, and then we're going to calculate that out. So our initial investment is going to be $3,000 at 2.5%. Remember, it's continuous, and I want to know how long it's going to take to double. And since we know that this is the continuous interest, we need to use the continuous interest compounded interest formula, which is A equals PE to the RT. And we know that we're going to double our $3,000, which of course makes $6,000. And so that's going to equal 3,000 e to the 0.025. Remember, we change our percents into decimals, 0.025 t. And then as before, in the last lesson, we want to isolate our exponential term. So we divide both sides by 3,000, and we get 2 equals e to the 0.025 t. And then in order to get rid of the e to the, and get the t down to our regular level where we'd like to be able to use our variables, we need to natural log both sides. So here we are, we've natural logged both sides. So we have the natural log of 2 equals 0.025 t. And then we go to our calculators, and we look up or calculate the natural log of 2, which is 0.693 equals 0.025 t. Divide both sides by 0.025, and presto changeo, we have t equals 27.7 years in order to double our $3,000 and make it into $6,000. So this problem's already worked out because I'd already started this video and realized that I needed my calculator, so I went and got the calculator, and so now I'm going to restart with the calculator. So while I'm doing my calculations, you can do your calculations, and we can both practice together. Alright, so that was the first line on the table. The second line, or maybe the third line, is going to look like this one. Find the amount after 10 years. So we have the same kind of situation here. We still have A equals PE to the RT. We still have $3,000 to start with. We still have 2.5%. So we're just going to plug in all that information again, and we want to find the amount after 10 years. So T is going to be 10. So we have A equals P, which is $3,000, E to the 0.025 times 10. I certainly don't need my calculator for that. So equals 3,000 times E to the 0.25. And then we go to find E to the 0.25. So I have second E, 0.25, enter. It'd be helpful if my calculator was on. So we have E to the 0.25, enter, which is 1.28. So equals 3,000 times 1.284 equals, so times 3,000, 123, equals $3,852.78. So that's going to be how much money we're going to have after 10 years. So these problems are pretty simple, just plugging in the numbers into the formula. Okay, same table, same formula, different numbers though, and different missing pieces. So we're going to start with $500, and we're going to go for, it says it'll take 8.5 years to double. Find the interest rate. It's the same thing, we use the same formula. So we start with A equals PE to the RT, And feel free, obviously, to pause the video anytime you need to so that people can catch up. And so we're going to double our money. So the principal is $500, and if we're going to double that, that means 1,000. So we have $1,000 here equals 500. E to the interest rate we don't know, so we'll put that as R. And the time is 8.5 years. So times 8.5. So as always, we need to, if we're going to solve for anything up here in the exponential area, we need to isolate the exponential term. So we're going to divide both sides by 500. So we'll get 2 equals e to the 8.5 r. And in order to get rid of the e, we need to natural log both sides, so we can bring the 8.5 r down. So the natural log of 2, which we already have looked up here, which is 0.693. So I'm going to do that over here. So we end up with 0.693 equals 8.5 r, because we got rid of the e there. And then we divide both sides by 8.5. So 0.693 divided by 8.5 equals 0.082. So R equals 0.082, or 8.2%. So pretty easy, just following the formula. And then using the same information, we want to find the amount after 10 years. Still using the formula. So I like writing the formula down when I'm teaching this stuff because it makes it easier for you to follow. P e to the RT. So we're going to put in $500, and we don't know the amount. So we have $500, e to the r, which is amount after 10 years. So we found the interest rate of 8.2%, so we're going to have 0.082, and the time is 10 years. So we got 10 right there. So we're going to multiply 10 by 0.082, which is 0.82. So A equals 500 e to the 0.82. So we go over to the calculator, and we do second e to the 0.82 equals 2.27. And we're going to multiply that by 500. And we have $1,135.25. So that's how much money we're going to have after 10 years. All right, so those are problems like 7 through 14. And actually we have one more that's in that category of that table, 7 through 14. And again, we're just looking for different things. This time we have the principal is $1,000, and we know that we have $1,200 after 10 years. We need to find the interest rate. So again, we just plug that straight into the formula and let the formula take care of all of our business. PE to the RT. So our principal is $1,000. Sorry, I didn't aim the camera very well there. We're going to have $1,200 after 10 years. So we have E to the R, we don't know, but we do know that T is 10. So we have 10R. So this is the same thing as before. So we just need to isolate the exponential term. So we divide 1,200 by 1,000, and we get 1.2 equals E to the 10R. And then again, bringing the getting rid of the e, the base, and bringing the exponent down so we can work with it. We natural log both sides because it's e to the. So we go over to the calculator and we do natural log of 1.2, and we get 0.182 equals 10r. Sorry, wasn't following along there. 0.182 equals 10r. Now divide both sides by 10, and we get r equals 0.0182, or 1.82%. And there we are. So I think you got the hang of this by now. And so I'm not actually going to do the time to double because, like I said, I think you got the hang of this. And we're going to move on to the next type of problem, which is very similar to numbers 17 and 18. So this is also a money type problem. And it says, determine the principal that must be invested at 7% APR, annual percentage rate, compounded quarterly, 4 times a year, for 30 years, so that there will be a $1 million available for retirement. So that's actually not too bad, but it may not be bad to have a little bit more than $1 million when you all retire. So in any case, we are going to do the compounded quarterly, so we need to make sure that we're using our proper formula. So we have A equals P times 1 plus R over N to the NT. And we need to know the principal. So P we don't know, but we know that A is going to be $1 million. So we put $1 million right here. 3, 1, 2, 3. So we have $1 million equals P. We don't know. 1 plus the rate is 7%, so we do 0.07. And this is happening N quarterly, so that's 4 here. And then it's N times T, so it's quarterly, 4 times T, 30 years, so 4 times 30 years is 120 to the 120th power. So over to the calculator, and we're going to divide 0.07 divided by 4. So 0.07 divided by 4 equals, and I'm going to add 1, and then I'm going to raise that to the 120th power. 120. And that gives me 8.019. So I have equals P times 8.019, and that's going to be $1 million. And so we divide both sides by 8.019, and we have our principal. So 1, 2, 3, $1 million divided by 8.019, and we have to invest $124,000. So P equals $124,000. $124,703,000.83. So, but that's not usually the way this works. You don't usually just put in a big lump sum at the very beginning of your retirement account. You usually start with an initial investment of maybe $1,000, or maybe just starting with $250, and you just keep adding, $250 a month or something like that, and eventually it accumulates pretty well. So that's like 17 and 18. So a problem similar to number 19 is, again, this is going to be a money and investment problem. So how long will it take P dollars, this time I don't tell you exactly how much it is, it's just P dollars, to triple at 4% interest compounded continuously? Well, we ought to start with a nice easy value for P, and I think that we should start with just $1 because that's the easiest thing to work with. And we're going to be compounding continuously, so again we're using our favorite A equals PE to the RT. But we're going to start with P dollars, and I'm going to suggest, like I said, $1. Make your calculations easy. And we're going to triple. So if we triple $1, we're going to make it into $3. So $3 at the end, $1 to start with, E, and we have 4%, so we do 0.04 T. And this is easy enough. We don't need to even worry about the 1. So we're just going to, you guessed it, natural log both sides, and then solve for T. So over to the calculator, hit the natural log button, 3, enter, and we get 1.099, there I go again, not following the pen here, 1.099 equals 0.04 T, and then we're going to divide by 0.04, and we'll have our time. So divide by 0.04 equals 27.47 years. So T equals 27.47 years. My soccer players will tell you the same thing, that I have trouble following. I'm just watching the game and not following the game or following the camera. So let's move on. Let's move on to a half-life kind of problem. So in problems like 25 and 30, we have a half-life problem where it says that the half-life of radium-226 is 1,599 years. If there was 12 grams initially, how much will there be after 1,000 years? Well, we already remember our half-life formula, at least I hope that we do anyway. So the amount equals, I'm going to say p again because we like to use p for our initial amount because it reminds us of principal. Half-life, well, it's half then, obviously. And then we do the time over the half-life, which is 1599. And so we're going to start with 12 grams, and we're going to go for 1,000 years, and we're going to figure out how much we have at the end. So here we have 12 grams times 1/2 to the 1,000 over 1599. So over to the calculator, we're going to divide 1,000 by 1599, and then raise 1/2 to that power, and multiply by 12. So 1,000 divided by 1599 equals 0.6254. So here we have equals 12 to the 12 times 1/2 to the 0.6254. So then let's calculate half to the 0.6254. So 0.5 to the 0.6254 equals, that's 0.6482. And we multiply that by 12. So times 12 equals 7.78 grams of the material at the end. That's our amount. At the end of how long? 1,000 years. So we've done some half-life problems before. This one shouldn't be too difficult. And let's do another one similarly. And this one's also a table kind of problem. That's the way it's going to appear in your book, just like the first ones did. The first ones we did today in these notes. So this is also going to be a table. So here's kind of the second or third line of the table right here. So the half-life of carbon-14 is 5,215 years. If there are 2 grams of carbon-14 left after 1,000 years, how much was there initially? So we just go back to the formula and plug in the stuff. So we have A equals P times 1/2 to the T over, different number this time, 5215. So we know that there are 2 grams at the end, so that goes here, that's at the end. We just want to figure out how much there was initially. So P we're going to calculate. And then we have 1/2, and we still have 1,000 years again, divided by 5215. So over to the calculator, and 1,000 divided by 5215, and we get 0.1918. So equals 2 equals P times 1/2 to the 0.1918. So we raise 1/2 to the 0.1918. So 0.5 to the 0.1918 equals 0.8755. So 2 equals 0.8755 P, and divide both sides by 0.8755. So 2 divided by 0.8755, and we have our initial amount is 2.284 grams. So it's a good thing that we started with more than we ended with. So we started with 2.28 and we ended with 2. As you can see, carbon doesn't break down as quickly as, or radioactive carbon doesn't break down as quickly as radioactive radium, because the 2 half-lives are different. Okay, so now we move on to a different kind of problem where we're going to have to do almost some modeling, and hopefully we're going to do some modeling a little bit later on when we have a little bit extra time, hopefully, which may or may never happen. Okay, so in 33 and 34, it says to create an exponential model in the form of y equals a e to the kt. Now you'll notice this just looks like a equals p e to the rt. It's the same kind of thing, only this is totally generic. It's not having to do with money, or maybe it has to do with money, but we're just going to leave it as just numbers here. So anyway, so we're going to create a model that contains the 2 points, 0, 6, and 5, 8. Now if this was just a straight line, we would just calculate the slope and then use y equals mx plus b because that would be a linear model. But we're not talking about a linear model here, we're talking about an exponential growth model. And then the next one down here, we're going to do an exponential decay model, as you can see. And we know this is growth because at 0 time, we started at 6. And 5 units later, could be 5 minutes, 5 hours, 5 whatever later, we're at 8. So we went from 6 to 8, so that means we did some growth. Now we remember from our a equals p e to the rt that the number in front of e is really just the initial value. Well, we happen to know the initial value here because we were given it. We know that at 0, we're at 6. So we already can calculate our a. This is one of our missing pieces here. So let's just start with our formula. Again, there it is right there. So we're going to start with y equals a e to the kt. And this is our y here, and this is our x. T is like our x here. And so in this case, we're going to be able to figure out a because it's really simple. It's just right there. So we're partway there. We already have y equals 6e to the kt. So we're partway done with our model. Once we figure out the k, then this will look like the kinds of things we've seen before. So it would be like find the amount after, or the amount when we've invested $6 at a certain percent. So we're actually trying to find that percent right now. So the way we're going to do that is we're going to fill in. So right now we have 1, 2, 3 variables, but we have another point that gives us 2 pieces of information to fill into the 2 variables. So our y is 8, so we're just going to plug that in here. So 8 equals 6e to the k. Well, we don't know k yet, but we do know t, which is 5. That's like our x. So it's 5k. Well, here we are again where we have an exponential piece, and it's not quite isolated yet, so we're going to divide both sides by 6. So 8 divided by 6 is 4/3, or 1.3 repeating, equals e to the 5k. And this is an e, or an exponential function with e as the base. So in order to get rid of that base, we need to natural log both sides and bring that 5k right down. So we're going to natural log 1.3 repeating. And the way I'm going to do that, of course, is go to the calculator, natural log, and I'm going to do 1 point, lots of 3's, and hit enter. And so I get 0.2877, calculated with 4 decimals here, equals 5k. And now I'm going to divide by 5. So I didn't change my calculator any. So divide by 5, hit enter, and I have k equals 0.058. So now the model is, now I can complete the model because now I got k and I have a, it's right here. So now here's the model, the final answer, which is y equals a, which is 6, e to the k, which we calculated to be 0.058, 0.058t. So that's how to create an exponential model if we have 2 points. And this was convenient because one of our points was the initial value. Now we're going to do one in which we don't have an initial value. We have 2 points that are kind of in the middle of the exponential function. And if you remember, I'm just going to draw a little graph over here. If you remember making scatter plots, you had a whole bunch of points, and what you did is you fit the best line into those points. Well, now what we're going to do is we're going to have a point like 1, 9 right here. I'm just going to put a generic point there. And 4, 7 is over here a little bit. Now instead of fitting a straight line through these two, we're going to fit an exponential function through these two. And so we, of course, all remember what exponential functions look like. So our exponential function is going to come down like this. And you can see how it's nice and curvy and getting a little flatter as we move down towards the x-axis. So that's basically what we're doing here. We're creating a function that is an exponential function. We're just trying to figure out what this curve is going to be using these 2 points. So again, we start out with the same formula that we started out with before. And we have y equals a e to the kt. And now we're going to use one of our points here. Well, actually, we're going to use both of our points at the same time, more or less. So let's plug in 9 and 1 and see what we get. So we have 9 for y. 9 equals a e to the 1 times k, because t is really our x. So we got 1 times k. And this is an a right here. This is 9a. And then we're going to get another expression from this one right here, 4 and 7. So we're going to get 7 equals a e to the, what is this, 4k. And so now we see that we have two expressions here, and we see that if we took these two expressions and divided them, which is exactly what we're going to do, if we divide them, we're going to end up getting rid of our a. So our a's are going to cancel off right here. So we're going to have, so you can see them canceling right off this big fraction here. Oh, sorry. So then we're going to divide 9 by 7. So we're going to go over to the calculator, and we're going to 9 divided by 7 equals, so we got 1.286 equals e to the, now we know that when we're dividing here, we got e to the 1k divided by e to the 4k is e to the negative 3k. So we're on our way to finding k here. So now in order to find k, we need to natural log both sides, just like we have several times. I'm going to go over to the calculator, and I'm going to natural log that number that we just had there, 1.286, and I get 0.2515 equals negative 3k, and I divide both sides by negative 3, and so I'm dividing by negative 3. Oh, try that again. So let's clear that away. So divided by negative 3 equals, so k equals negative 0.084. And that should make sense to you that, that this is negative because we're having a decay. So this is decreasing. So it's decreasing by like 8% or 8.4%. So now all that's left to find is the a, the initial amount. So now that we have k, we're going to plug that into our formula right here and use one of our points, and we're going to be able to get t. So let's use 1,9 because that's pretty easy. So we're going to have 9 equals a e, and then we got 1, and we got 0.084, so we got negative 0.084 times t, which is 1. So that's negative 0.084, of course. So now we do e to the negative 0.084. So here we are. So second log, so e to the negative 0.084 equals 0.919. So 9 equals a times 0.919. And then we divide 9 by 0.919. So 9 divided by 0.919 equals, we get 9.79. So a equals 9.79. So our final model is y equals, our initial value now is a, 9.79 e to the negative 0.084 t. There it is right there. Y equals 9.79 e to the negative 0.084 t. And again, this makes sense because we're having a decay. It's going down. So that's our negative exponent. And we should be starting above 9, because here's 9 right here. And our initial value has got to be above that, so it's right there. So 9.79 seems pretty reasonable for that. And we're going on to the second to last page here. And we have a fun problem here. I'm sure you'll be able to catch the reference right here. So here it is. The value of the famous, this is for problems like 37 through 40 on your homework problems. So the value of the famous leopard lady painting is given by V equals 50e to the kt, where V is the value in cents. Yes, you heard me, cents. And T is the number of years since 2011. In 2013, the painting, sold for 40 cents. Find K, and then predict the value of the painting in the year 2020. So this is actually going to have some similarities to the previous problem. So we got to find K, just like we did in the previous problem. And fortunately, we're given enough information to do that. So we know that in 2013, which is 2 years since 2011, the painting sold for 40 cents. So we're going to plug all the information in. So we have V equals 50 e to the kt, And we know the value was 40 cents. And we started at 50 cents equals e to the k we don't know, but t we do. T is 2 years. From 2011 to 2013 is 2 years. So 2k. And again, we've seen this whole situation before several times, so we're going to divide both sides by 50. So that's going to be 0.8 equals e to the 2k. And so we isolated our exponential term. Now we natural log both sides. Over to the calculator, natural log 0.8 equals negative 0.223 equals 2k. Divide both sides by 2 and divide by 2, and we have k equals negative 0.112. And again, you can see that the painting started at 50 cents. It was worth 50 cents initially. There it is right there, 50 cents initially. And a little later on, it was worth 40 cents. So you can see that the value of the painting is decreasing. Sorry, Sarah, your painting value is decreasing. So it's decreasing right here, and so we have a negative. It's decreasing by 11% per year. So now we should predict how much the painting is going to be worth in the year 2020, which is 9 years since 2011. So our value, which we don't know, so value equals 50, which is our starting value, e, and now we have k, which is negative 11%, negative 0.112, and we have 9 years from 2011 to 2020, so times 9. So we're going to multiply 0.112 times 9, so multiply times 9 equals, so we have negative 1.004, so equals 50 e to the negative 1.004, and so we have second e to the negative 1.004 equals, so equals 50 times 0.366, and so times 50 equals 18.32 cents. So that's how much that great painting is worth in the year 2020, 18.32 cents. So this problem is very similar to 37 to 40. Those don't necessarily have to do with paintings, but they do have to do with this kind of use of the formula, the PERT formula, basically. All right, and our last problem. So here it is. This one's like number 42. An ancient wooden carving has 20% as much carbon-14 as a new wood carving. How old is the ancient wood carving? So we're looking at carbon-14 here, so that should tip you off that this is a half-life problem. So we do A equals P times 1/2 to the T over half-life of carbon-14 is 5715. We had that in a problem earlier. And so we know that we have 20% as much carbon-14 as we started with. Well, again, if we're going to use some easy numbers for ourselves to work with, if we know that we're going to start with 20%, then we could have 0.2 for the amount at the end and 1 for the amount at the beginning. So we'll have 1 gram of the stuff at the beginning, just to make our lives easy. So we have 0.2 at the end. 1 is how much we're going to, is the amount that we're going to start with and calculate with, because that makes our lives easy. And then we have 1/2 T5715. So again, we're just trying to fill in as much of the stuff as we can with easy numbers if we can do that. So again, it's 20%, so we're going to use 0.2 and 1 here. We could use other numbers if we wanted to. We could have used 100 and 20 right here, but either way, we're still going to have to divide by 100, so we get 0.2 anyway. So here we have our 0.2, 1/2 T to the 5,700, or T over 5,715. So again, we have an exponential equation here. So in order to bring this T right down to its regular level, the one that we like to calculate with, we need to natural log both sides. Or we could common log, but again, as I've suggested, natural log is the more universal approach. So we're going to write ln of 0.2 equals ln of 1/2 to the t over 5715. And we know that when we have a log of something to a power, we know we can bring the power down in front, and that's what we're going to do here. So we're going to have the natural log of 0.2 equals t over 5715 times the natural log of 1/2. So a little quick calculator work here. So over here, so we have let's clear that. Natural log 0.2 equals negative 1.609 equals, let's do the natural log of 1/2. So natural log 0.5 equals negative 0.693 times t over 5715. That's supposed to be a 5 there. And then we're going to divide both sides by 0.693 to get that over to here and isolate the t and the variable there. So divide negative 1.609 divided by negative 0.693. So negative 1.609 divided by negative 0.693 equals, so we get 2.322 equals t over 5715. Now all that's left to do is multiply both sides by 5715 times 5715. Enter, and we get t equals 13,269 years old. So our wood carving is 13,269 years old. And this is about how that works. You know, they're able to take a sample and figure out how much carbon-14 is in that particular sample of this ancient artifact, and then compare it to how much there would be in a new artifact of the same type of wood, and then plug into the formula, and this is how they calculate how old a piece of artifact is. And if it's significantly older than you know, maybe 5 or 6 or 7 times 5,000 years, then they use something other than carbon-14. All right, so there ends the lesson, and at the end of every lesson, of course, is the assignment. So here it is. It's page 264, 8 to 18 even, 26 to 24 the evens, and then 37 to 40 and number 42. This should be great fun and not too difficult, I don't think. I think it was a pretty easy lesson. So enjoy that, and I'll see you next week. Thanks.